Hello everyone, this is Shankhu Shubhra Rai Karmakar and welcome to my channel, that is Reverberation Guidelines. So today we are going to discuss about Coulomb's law. In the previous chapter we have learned about several things about the basics of electrostatics, and this is the second part of electrostatics, and we will carry the total chapter up to electric field and electric potential and furthermore. But before we start, we will recall the previous topic, that is the fundamental statement of static electricity, that is the same type of charge repel each other and the opposite type of charges attract each other. You can see that the two laws or the two statements which have been delivered in the previous lecture, where the same type of charges repel each other. That means a positive charge will always repel the other positive one and the negative charge will always repel the other negative one. But there will be an attractional force between a positive and a negative one. That is, a positive charge will always attract a negative one and a negative charge will attract a positive one. And the amount of force which are going to be acted between on a charged particle with respect to the other charged particle is going to be measured with the help of the Coulomb's law. Before we describe the Coulomb's law furthermore, we need to know about some properties on Coulomb's law. So the properties number one, that is the force of attraction or repulsion between two charged particles will always works across the line of joining. That means we are considering two charged particles, one be Q and another be Q dash. And we are not interested to know the proper property of the charges. They may be positive, they may be negative. So if both of them are same type of charge, they will repel. If one of them are positive and another is negative, then they will attract. We are not interested to know about the type of attraction or type of forces, but the amount of force will always work across the line of joining. That is the first property of the Coulomb's law. Number two, if there are two objects containing some amount of charge, then the objects will be considered as point charges. The charged objects will be considered as point charges. Number three, right? So in the point number three, the Coulomb's law explains a type of force, and such type of force is always conservative force. So the force of electrostatics is conservative in nature. Number four, theoretically the extension or the range of the electrostatic force tends up to infinity. So theoretically it is possible, it is not possible practically. So theoretically the extension of electrostatic force tends up to infinity. So these are the properties which we need to know about Coulomb's law. An interesting part is going to be discussed, that is the spherical symmetry of electrostatics. We know
that the force of attraction or repulsion between two charged particles is inversely proportional with the square of their intermediate distances.
So now we are thinking that two charged particles, one is Q and another is Q dash, are placed at a distance of r. Now, centering one charged particle, let us imagine a Q. We are imagining a spherical surface of radius r. So, it will look like a sphere where the center it is containing the amount of charge Q and the radius of the sphere dr. So, we can place Q dash at any point of the sphere. Let us imagine here, anywhere of the sphere, on the upper surface of the sphere. So, the intermediate distance between two charges will be same. As a result, the force of repulsion or attraction must be same. This is nothing but the spherical symmetry of electrostatics. Now, we are expressing the statement of Coulomb's law. And Coulomb's law is stating that the force of attraction or repulsion between two stationary charges, the force of attraction or repulsion between two point static charges is directly proportional with the product of their charges and inversely proportional with the square of their distance. Now we are going to concentrate on the charged object which are going to be denoted as point charges. So the charges must be the point charges and they will be concentrated as a static one. So now we are imagining 2 point charges. One is Q and another is Q dashed. So one may be Q and another may be Q dashed, whatever may be. It can be assumed as Q1, Q2, whatever you want. But we are not interested about the type of charges. So they may be same type of charges where the repulsive force will be activated. They may be the opposite type of charges where the attractional force will be activated. But the charges containing the values of Q and Q dash and the intermediate distance between them let be r. So the charges be Q and Q dash and the distance between them be r. So the force of attraction or repulsion is directly proportional with the product of their charges, that is Q, Q dash, and inversely proportional with the square of their distance, so that is 1 by r square. So using the variation, we can write F proportional to Q, Q dash into 1 by r square, that is written as 1 by 4 pi epsilon naught into Q, Q dash by r square, where 1 by 4 pi epsilon naught is the constant. And we always try to calculate in SI process. So this is the constant in SI unit. So from Coulomb's law, we came to know about the thing about the total force of attraction or repulsion between two charged particles is going to be given as F equal to 1 by 4 pi epsilon naught into Q, Q dash by r square. And I told you earlier, 1 by 4 pi epsilon naught is the variation constant. And it has a value that is 9 into 10 to the power 9 Newton meter square per coulomb square. And we will later discuss about the dimension of epsilon naught and something more. But now what we need to concentrate, that is epsilon naught is known as the permittivity of free space. Be careful with the term. This is the permittivity of free space. Now, we are interested to find out the dimension of epsilon naught. And in class 11, we have done it several times, but still we are trying to find it out. So, F equal to 1 by 4 pi epsilon naught into Q dash by R square. So F is nothing but the force, and force is going to be given as mL t to the power minus 2. And for pi, that has no dimension at all. So epsilon naught into Q means IT and Q dash means again IT. So we can write it is IT square by this is L square. So epsilon naught is given as 1 by mL t to the power minus 2 into I square t square by L square. That can be written as m to the power minus 1, L to the power minus 3, t to the power 4, I square. And this is the dimension of the permittivity of free space. Now we are trying to define 1 coulomb. So before we define 1 coulomb, we are thinking about the previous lecture. So in the previous lecture, we told that the unit of charge in SI unit is 1 coulomb. So as a result, we are thinking that Q and Q dash both have the same value, and that is 1 coulomb. And the intermediate distance between two charged particles is going to be considered as R equal to 1 meter. So the force between two charged particles can be written as 1 by 4 pi epsilon naught into 1 by 1 square. So that is force equal to 9 into 10 to the power 9 meter. So now we are defining 1 coulomb in such way that two same type of charges placed at 1 meter distance, when they are able to realize the force of 9 into 10 to the power 9 Newton, then each of the forces are going to be calculated as 1 coulomb. Clear? In the same way, if we try to define or implement the CGS unit of charge, that is 1 stat coulomb or 1 ESU. So we are implementing the CGS unit. So in CGS unit, the force between two charged particles is given as Q dash by R square, where variation constant equal to 1 in air. So now Q and Q dash let be 1 ESU or 1 stat coulomb. That is Q equal to Q dash equal to 1 stat coulomb, and R equal to 1 centimeter. So then force will be 1 into 1 by 1 square, that is 1 dyne. So if we try to explain the CGS unit of charge, then we will write in such a way: when two same type of charges are placed at a certain distance of 1 centimeter, and if they realize 1 dyne force, then we can easily state that both of the charged particles are containing 1 ESU or 1 stat coulomb charges. The electrostatics and the gravitational force both have the same type of expression. For gravitational force, the expression looks like G into m by R square, and for electrostatics force, that is F equal to 1 by 4 pi epsilon naught Q dash by R square. So both look like same, but they have a huge difference. because this type of force is always attractive, but this may be attractive as well as repulsive. And this G is the universal gravitational constant. So it is universal constant. But this belongs to the permittivity of that particular space, where epsilon naught is the permittivity of free space. So epsilon is the permittivity of the space. Epsilon naught, permittivity of the free space. If two charges of Q and Q dash are placed at r distance in air, if two charges are placed at r distance in air, then the force of attraction will be 1 by 4 pi epsilon naught into q dash by r square. We know the epsilon naught is the permittivity of free space. So epsilon naught is the permittivity of free space or air, that may be considered also air. Now, if the intermediate air is going to be substituted by another material means that must be an insulator or a very poor conductor, means the intermediate air layer between two charged particles is replaced by another material, and I told you earlier the material must be insulator or very poor conductor, very poor conductor or insulator, right? Then the force of attraction or repulsion between the charged particle will be changed, and this would be 1 by 4 pi epsilon r into q dash by r square, where epsilon r is the permittivity of the substance which replaces the intermediate air between the charged particle. The substance which replaces the intermediate air layer is known as dielectric material. So the insulator or very poor conductor material which replaces the intermediate air between two charged particles is known as dielectric material. Dielectric material. And due to the replacement of the intermediate air layer with the substance, or that is going to be termed as dielectric material, the force of attraction between two charged particles will genuinely be reduced, and the amount of or the times of reduction is known as the dielectric constant of that material. So we can define the dielectric constant in such a way that the times of force of attraction or repulsion between two charged particles is going to be reduced with respect to air when the intermediate air layer is going to be replaced by the dielectric substance is known as the dielectric constant. So basically, if the total amount of force between two charged particles in air be F, and when the intermediate air layer is going to be replaced by a dielectric material, let us silica or water, then the force between two charged particles becomes, let be F dash, then the dielectric constant must be F by F dash. The dielectric constant is going to be defined as F by F dash, where F is the force between two charged particles in air, and F dash is the force between two charged particles when air is replaced by a dielectric material. So it seems like that 1 by 4 pi epsilon naught into q dash by r square divided by 1 by 4 pi epsilon r into q dash by r square. So minimize total equation, we get epsilon r by epsilon naught, that is dielectric constant. So dielectric constant K is given as the permittivity of the dielectric material by the permittivity of free space, or that can be defined as air. Clear? And we will implement such type of values in the next lectures.